My name is Kate Stockton, and I work in the Student Services Office for the Mechanical, Aerospace, and Nuclear Engineering Department. And today we're going to introduce you to one of our faculty members in the Mechanical Engineering Department, Dr. Sandy Mishra. So let me just introduce him and give you a little more background. So Professor Mishra joined RPI's faculty in the Mechanical, Aerospace, and Nuclear Engineering Department in fall of 2010. He was promoted to the associate professor with tenure in 2016. He was a member of the 2010 Japan MEXT NSF Young Investigator Exchange Program for Nano Manufacturing and the recipient of the NSF Early Career Award in 2013 on additive manufacturing. His research interests are in the area of systems and control theory, learning control, nonlinear estimation, and precision mechatronics as applied to additive manufacturing, unmanned aerial vehicles, and smart buildings. He is the principal investigator of the Isaac Laboratory at RPI, which is supported by grants from government agencies such as NSF, DoD, DOE, along with industrial partners including Hewlett-Packard, Sikorsky, MathWorks, National Instruments, Symmetrex, and Vivonics. Professor Mishra's teaching portfolio includes systems analysis techniques, feed-forward and learning algorithms, advanced manufacturing systems and processes, mechatronics, modeling and control of dynamic systems, and introduction to engineering analysis. He was a recipient of the Class of 1951 Teaching Award in 2015, the School of Engineering Education Innovation Award in 2017, the School of Engineering Research Team Award in 2017 and in 2019. So I just wanted to say again, welcome. I'm going to hand it over to Professor Mishra in a minute. And just let everybody know that if you do want to use them, there are closed captioning in the top right corner. You'll see the CC button. If you want to turn those on, feel free to ask any questions. Greg from admissions is going to moderate them. So if you don't see your question pop up, you don't need to enter it more than once. He's going to make sure that the questions get answered. So without further ado, let me turn it over to Professor Mishra.
Thanks, Kate. So welcome, everybody. What I'll do is, Kate mentioned some of the things, some of the classes that I teach and the research that I do and so forth. And what I'd like to do is go over some of those things, my interactions with the students, the opportunities that students and I have in terms of working together, clubs and so forth that are related to the stuff that I do on campus. I'll go over all that in a few slides. So Kate mentioned this earlier, but the classes that I teach generally fall under the broad umbrella of what we call systems, dynamical systems and control. So at the freshman level, I teach a class called Introduction to Engineering Analysis. In this class, the students learn about linear algebra, how it's applied to engineering systems, civil engineering systems, mechanical engineering systems, electrical engineering systems, depending on what your major is. Introduction to Engineering Analysis kind of covers the application of fundamental linear algebra tools to engineering problems. At the junior/senior level, I teach a class, a required class for all mechanical, aero, and nuclear engineers called Modeling and Control of Dynamical Systems. In this class, what we learn about is when you have a physical system, let's say you have a car, how do you model it? And when you mean, what does this model do for you, right? What does it tell you? And once you have a model, how do you use that model to control it? Now, of course, if you have a car, you want it to drive, let's say it's an autonomous vehicle, you want it to keep its lane, you want to keep its cruise speed, whatever it might be, its maneuverability. So we design controllers that enable these properties, this autonomy for a dynamical system and an engineering system in general. At the senior level, I teach two classes, mechatronics and capstone design. Capstone design is sort of the culmination of your design experience, putting together everything that you've learned throughout your 4 years, all the way from freshman level concepts to tools that you've learned in your sophomore and junior years, and then the advanced classes that you've taken, let's say like mechatronics. You put all of those things together to address a design problem that is often sponsored by an industrial member affiliate, or it could be something that's on campus that's a research project. So it depends, but you pick up a design problem in a group of 6 or 7 students and you try to solve it, and it's usually a semester-long project. At the graduate level, I teach systems analysis techniques and feed-forward learning. These are more advanced courses that you can take if you have interest, or if you want to do a co-terminal program and so forth. But we'll not talk too much about that. The one class that's my favorite to teach is mechatronics. It's a senior level class. The reason why I like it is because you get to make your own little baby Segway. You get the components, and like I'm showing you a video of at the end of the semester, you build your own Segway. Everybody's got their own design strategy in terms of not so much the physical, not necessarily the physical components, but the intelligence that goes into it, right? So how do you make the Segway balance itself? It's got lots of sensors on it. It's got a motor. Its objective is to balance itself and then move in a certain way. And the students try to have all kinds of competitions where they try to see if they bump and keep each other still upright. In this case, you can see the two students trying to, and this is all autonomous, right? So nobody's controlling these. There's nobody with a joystick. It's all purely driven by the intelligence that's been programmed into the system itself. And so the students learn how to integrate the mechanical components, mechanical modeling with electronics. These have Arduino boards on them that do the processing and so forth. And then you get to have fun. And I really enjoy teaching this class because you get to, each of these, by the way, these kits are all taken home by the students, and they get to work on those kits through the entire semester. And then at the end of the semester, you turn in your final project. So that's, again, this is the culmination. We have another project also in mechatronics, which I'm not going to be sharing today necessarily with you, which is a magnetic levitation system. So there you're trying to make something fly in midair using a magnet. From a research standpoint, I'm the PI, as Kate mentioned, of the ISAC lab. It stands for, the ISAC is short for Intelligent Systems Automation and Control Lab. And the central theme of what we do in terms of a research standpoint is autonomy and control, right? And we see more and more systems, engineering systems becoming autonomous. So you're embedding intelligence into these systems, be it smart buildings, unmanned aerial vehicles, you have drones, 3D printing, additive manufacturing of by making metal parts. So all of these, at the heart of all of this, the thing that I'm most interested in is how do you embed intelligence into these? So that's a combination of algorithms, that's the computer sciencey part of it. There's software hardware interfacing, which is the electronics/electrical engineering piece of it. And then there's the mechanical system itself that you're trying to control. And that's the mechy side of it, right? So the stuff that I do in my group lies at the intersection of mechanical engineering, electrical engineering, and computer systems and algorithms. And of course, the types of problems we look at they're domain agnostic, like all kinds of interesting problems. Anything that you can put a brain on, that's what we like to do. It'll just give you a couple of examples now of the types of projects that we do. All the ones I'm going to talk about today are all undergraduate related projects. Okay, so I'm not really necessarily focusing on the graduate level problems, just more the kinds of undergraduate research projects that students tend to do in my group. So the first one was this project that we did a few years ago on flying an aerial vehicle through a very tight space. Okay, so here you can see that there is an opening, right? And there's a quadcopter that needs to fly through this opening autonomously. So there's no joystick, there's no nothing. We press a button, the UAV senses its environment. In this case, it senses, let's say, an opening that's moving in sort of rotating back and forth. Then it predicts the motion and then tries to fly through it. And you can see that the clearance is pretty small. It's about maybe 1.5 inches on either side, and it's flying pretty fast, right? So it's a very challenging problem. And the application of something like this is for example, in search and rescue, right? You're trying to find something. Let's say there's you need to locate something that's inside a burning, let's say, building. You want to fly in, fly out. It's a tight window, right? And things might be moving and so forth, and you would like to fly through it autonomously. So there's no pilot here. So the second video that you're seeing is the same kind of thing now, except the motion is a little different, right? Instead of now a rotating window, you have a laterally moving window that the vehicle senses, and then it charts a path through, and then as fast as it can, flies through that window. And then you can see the tilt again. It needs to fly almost at a tilt as it's going through that window. Another project that is also in sort of the aerial vehicle universe is this idea of a modular aerial vehicle. So in this problem, what the students were trying to do is they were trying to understand, how can I arrange, let's say I have 6 rotors, right? In this case, you see 6 rotors on the left arranged in like a flower pattern, in the middle in like a delta pattern, and on the side in an S pattern. Right? The same number of rotors. And we would like to know which of these is a good way to arrange these rotors. Right? What kind of properties do we see if you have different orientation / organization of these single rotors? And I'll start with this video first, which has a very compact 6 rotors flying. You can see it's very stable, right? Extremely stable. It flies, and somebody just bumped it with their foot, and it's got good flying properties. One of the problems with when you have 6 rotors like this is if one of the rotors fails, then this aircraft will fall. There is actually no robustness to failure built in. The second was the flower pattern. And this flower pattern, you'll notice that the flight is pretty stable, not as stable as the delta pattern. It's a little bit kind of wobbles around a little bit more. But the nice thing about this is that if one of the rotors fails, then this aerial vehicle will still fly. It has some robustness to failure of a single motor. It won't fly as nicely as before, but it certainly will survive. And then finally, the third example was one that had, I can't play this video for some reason. I guess that doesn't work. But in the third pattern, which was the S-shaped one, you would have noticed that this tends to have very poor balancing. It does actually flops around quite a bit. And if one of the rotors fails, it'll actually also fall down. So it has sort of the worst of the 2 worlds in this case. So the bottom line is that the students get to understand, first of all, design these experiments to figure out how to build a single rotor. How do you put them all together? And then once you do put them together, what's the best way to put them together? And then once you have put them all together, how do you assess whether or not it is a good arrangement of the rotors? And of course, at the end of it, there's all autonomy, right? We're trying to fly all of these things autonomously. A second project, this was a few years ago, we were tasked by the Army Research Lab to come up with a mechanism to 3D print organs that are not biologically functional. So these are actually not a functional heart or a functional kidney. Instead, they are meant to be surgical replacements so that a surgeon can practice a surgery before doing the final version of it on a patient, right? So it's a custom model for training a surgeon before the surgery is actually performed. The reason why so this project was about maybe a year, 2 in length, And it involved 5 undergraduate students, 1 freshman, 3 juniors, and a senior. And they came up with a 3D printer that could essentially print structures that had the same texture as a human organ. They didn't have the biological functionality, but they felt like the close enough in some sense to how an organ would feel. And part of the reason why we wanted to do that was because surgeons rely very heavily, not just on visual feedback, but also how the texture of what they are cutting through is, and what that texture is. That feedback is important for them to guide their surgery. So they came up with this method of inkjet printing, layer upon layer, and then in between layers of inkjet printed material, they would deposit fibers. And the reason why they deposit the fibers in between the layers of inkjet printing, so here you can see the first layer got printed. We're going to move out to the side, and then we'll come down and stamp. Here you can see a stamping of the fiber, then it gets withdrawn, and then it comes back, and then you print the next layer on top. And as I mentioned before, the reason why fibers are particularly useful in mimicking human tissue texture is because human tissue itself has collagen and elastin fibers, which is what give it its structural properties. So it was a project that was, again, 5 undergraduate students spent a year and a half on it. And we went on to deliver this process to the Army for deployment, and hopefully they're doing something with it. In terms of the other interactions with students and student groups on campus, I have worked in the past with the Rensselaer electric vehicle team, and I'm currently involved with the ASME chapter at RPI. I'm the advisor for the robotics team. And in these clubs are pretty autonomous. They get to choose what kinds of competitions they want to participate in, how they want to organize on campus. And the advisor's role is primarily to look at the functioning, right, of and ratifying and approving actions, purchases, things like that. In addition to obviously giving technical input on how to solve certain engineering problems. So again, this is, if you're interested in any club-related activities, there's a lot of fun clubs on campus. There's Design, Build, Fly. That's an aero club. There's the electric vehicle team. There's a hybrid team. There's a Formula One team. All of these clubs on campus are very active, and they're all pretty closely tied with faculty involvement as well. And finally, I'd like to say that the best part, and this is true, I think, both for students and for faculty, the best part about being at RPI is that you become a part of a family, right? And I'm just showing here just students that I have worked with very closely, right, over the past 10 years, where they are today. And they're all over the US. They're all these companies, startups, they're at universities. And the best thing you get out of your college, the degree is what it is, but really it's the connections you build with, in my case, the students that I have had over the past 10 years at all these fantastic places doing great things, and building that network and keeping it alive. Many times, a lot of students will come back a year or two later. Sometimes they're recruiting. Sometimes they come back 5 or 6 years later. And the nicest part of my experience is getting to see them grow and go out and do fun things. So with that, I will open it up to questions that you may have. I think there's a whole bunch of these questions on the left, and I think Greg is probably going to answer most of them, but I'm more than happy to respond to anything that you're interested in.
Hello, everybody. So I've been going through some of your questions. I'll continue to answer the admissions ones, but we have one. What's the CAD software?
I think SolidWorks is the one that most at capstone level, that's what I see most frequently.
Perfect. And then this is the next question. So hands-on learning since freshman year, or is it you have to wait until your junior year? So how early do students start the hands-on work?
At the